Okay, the 2009 question 5 exam. So a vanadium redox battery is used to store electrical energy generated at a wind farm in Tasmania. The battery supplies electricity to the power grid as required through a control switch. So it's charged, it's recharged with the wind turbine, and then it's discharged to power the grid. The reactant is stored in an acidic solution, so you have hydrogen ions around in large tanks and pumped through the cell. The cell is recharged using electricity generated by the wind turbines. So electricity is coming out here, and then it's being put back in. Polymer membrane allows the movement of particular ions. So the membrane here allows particular ions. Because it's got it's an acidic solution, those particular ions would be hydrogen ions. Okay. The two relevant half equations for the vanadium redox battery are these two. Whenever you're given equations, just check. So they're written like the electrochemical series with the electrons on the left, so they're both reduction reactions. Just make sure that this is more positive than that. So if they're both negative, then the smallest negative would be on top and the biggest negative on the bottom. So the more positive one needs to be on top. So these are in the correct order, so you don't have to worry about rearranging them. If they are, I recommend that you rewrite them because it just gets too confusing. Same order as electrochemical series. Okay, so if they're in the same order, then the chemicals on the left undergo reduction. This particular chemical, I should have just circled it. It's undergoing reduction, and it forces something below it to undergo oxidation. So this is undergoing reduction, and this is going to undergo oxidation. State the polarity of each electrode as the battery is discharged. So as it's acting spontaneously, galvanic like this, discharged, these are the reactions that would happen. So state the polarity of each electrode when this is happening. So we've got the VO2. Be careful, there's VO2 plus, and there's VO2 plus. So VO2 plus. This chemical is getting the electrons, and the VO2 plus is losing them. V2 plus. So it's undergoing oxidation, it's losing them. So the electrons are being lost from here. From here, I should have circled this. So electrons are being lost from here, going around, going up to power your whatever, coming back and going over to here. And then being this is receiving them. So we're going from here to here. This is a storage tank to keep adding this chemical and adding this chemical. Okay, so state the polarity of each electrode as it's being discharged. Electrode B is where they're coming from. Remember to set up your little anode, cathode, galvanic, electrolytical, recharge. So this is galvanic is spontaneous, it's discharge, and electrolytic is when it's being recharged. Okay. So this one is always negative. Spontaneous anode oxidation is the loss, reduction is the gain. It's always negative. So once you know that, then that's positive. And it's reversed. Okay, so B is where the electrons are coming from. B is where oxidation is happening. It's the anode. It's negative. B is negative. Therefore, A is positive. Okay, so you just have to work your way through this. Where are the electrons coming from? That's where the anode is. It's oxidation. It's negative for normal discharge. Okay. Circle the vanadium containing ion that would have the highest concentration at the anode. Oxidation. Here. Here. So the one that would have the highest amount would be the B2+. Okay. Just pause it for a second. Okay, write a balanced overall equation for the reaction that occurs when the cell is being recharged. So recharged is the opposite. This is discharged reactions, the ones that I've circled. I'll do this really slowly, the long way, but once you get good at these, you can just kind of skip. So we're looking at the opposite to that. So if I write this out properly, discharge reaction would be the VO2 plus 2 VO2 plus H2O, and then this you write around the other way. You write it, pick this up, flip it over, so that you're writing it as an oxidation reaction, and then you put everything on the left together as the reactants and everything on the right together as the products. Notice that there's electrons on this side, electrons on that side. When you put the two half equations together, the first thing that you have to make sure is that you have the same number of electrons. So you've got VO2 plus 2H plus electrons plus this, making VO2 plus the water plus the V3 plus the electrons. Then you cancel out the electrons, and that is your discharge reaction. Okay, so recharge, it's just the opposite. These chemicals were the products, now they're going to turn back into the reactants. So you just write it out the other way. Just be careful what you're writing. Plus the water plus V3 plus, forming VO2 plus 2H plus V2 plus. Okay. When you do this, make sure you have your states and that you're not getting these things confused. Alright, so rather than writing that nicely in the spot it's supposed to go in, because it just takes forever. So this is the recharge reaction. Make sure you've got all your states in, and you can check on your on the question to make sure what the states are. Okay, compare the vanadium redox cell to a fuel cell by describing one major way in which they differ. So there's lots and lots of ways in which this is different to a normal fuel cell. So a normal fuel cell, you continuously supply the fuel like this, but you don't recharge. So the electrons are always going from the chemical that's losing them to the chemical that's gaining them. They're always going this way, you're always putting more in. So you're continuously supplying new reactants. You don't turn the product here back into this. Okay, so this is different because we can put the electrons, force the electrons to go back this way. So normally they would go here, out here, around and back, and then over there. So kind of on their way over to here, they're powering the grid. Or the windmill can force the electrons to come back this way. So it's dragging them from here, up, around, and over and down, forcing them to come back this way. So that's the classic sort of answer to this question. One major way is that fuel cells are continuous reactants, but you don't recharge them, whereas this one you can. So continuous supply. A fuel cell, you use molecules, hydrogen, methanol, whereas this is ions. We don't normally have ions. Okay, that might be enough. So, write a balanced overall equation to show why iron would be an unsuitable material to use as electrode B in the vanadium redox cell. So why should we not use iron here? Okay, let's get some fresh paper. Okay, so if you look up the data booklet, you see that iron is down here, and it has an E0 of negative 44. Make sure you're using this iron. This iron is the solid to use as an electrode, solid electrode. Don't use this. These are iron, both ions. Okay, so don't get those confused. Alright, so if we use this one, it's negative 44. Okay, so if you look back at the equations that you were given, you can see that negative 44, this is more positive, negative 255 is less negative than negative 44. So if you write them out in order, we've got this one, VO2 plus 2, oops, electrons, plus 4 volts, and the one that we had reacting before, 2 plus, and now we have our iron solid, and Fe3 plus electrons coming out of the 0.25. Okay. Alright, so these ones, normally this was reacting with this. This was undergoing reduction, that was undergoing oxidation. This is in the same place as the electrode B would be with the iron. So these are reducing agents. So anything below is a stronger reducing agent. As far up as you go here, it's the strongest oxidizing agent. So iron is a stronger reducing agent than the vanadium 2 plus. So the iron in here would lose the electrons rather than this. So the iron would undergo oxidation rather than that one. So the question asks you to write out an overall equation to show why iron would be unsuitable. So you would put these two together. So if we turn it, write it around the right way, iron solid, 3 plus 2 plus, sorry, plus an electron. So we're putting this and this together. So to be VO2 plus 2H plus. The first thing you need to make sure is that you have, and I haven't written the right number of electrons here, make sure the electron numbers are balanced. So this entire thing at the top needs to be multiplied by 2 because you have 1 electron and this has 2, which means we need 2 of these and 4 of those. Let's haste 2 electrons. Okay, so everything on the left plus iron solid, making 2 of those, 2VO2 plus 2 of those. This 2 here, these are the ones that people forget, apart from me forgetting it to start with. And then this plus Fe2 plus 2 electrons, so everything on the right. Tidy it up, so cancel your electrons. Is there anything else we can tidy? No. Okay. So that's a reason why you wouldn't use iron, because it would undergo oxidation instead of the vanadium. You could also, this would also react with that in the cell itself. So because this is a stronger oxidizing agent than that, the VO3 plus that's in there would directly react with the iron. So the iron would lose electrons over to here instead of the V2 plus, and the iron would directly react with this. Okay, directly react and react. So the iron electrode would gradually get eroded away and turn into ions. There was another equation that they accepted. In here we also have hydrogen ions. And if you look on your electrochemical series, the hydrogen ions are the 0, 1 here. Okay, so hydrogen H plus. So if we put that in our order, we have 0, it's -0. It's here. So your standard half cell, what a mess. H plus plus 2 electrons making H2 plus. So it would also react. So any of those they accepted. This one with the iron, this one with the iron, or this one with the iron. As this is the strongest oxidizing agent, this one would be the most favoured. Okay.